спекуляции, которые, one of the most wonderful things about science is that it allows us to imagine things that sound completely impossible and then go out and find that they're actually real. The idea, what if everything you see, this world, these atoms, even you, had a kind of mirror twin made of something completely opposite, not just different, fundamentally reversed. Matter, as we know it, makes up everything around us. But nature, it turns out, isn't satisfied with just one version of reality. It has another trick up its sleeve, antimatter. Now, antimatter isn't science fiction. It's not just something you hear about in movies. Terrible. And it follows the same laws of physics, but with a twist that's so strange, it almost feels like nature is playing a joke on us. Safat and I want to take you on a little journey, not to some faraway galaxy, but into the hidden symmetry of the universe to explore a simple but fascinating question. What is antimatter? One of the most wonderful things about science is that it lets us take ideas that seem completely absurd at first glance and then slowly, carefully, that they're not only possible, but actually part of the way the universe works. Like opening a door you didn't know existed, only to find an entire hidden world behind it. Now, when we look around, everything seems pretty straightforward. There are tables, chairs, people, planets, stars, all made of atoms, and for a long time, we thought that was the whole story. Atoms were the basic building blocks made up of protons, neutrons, and electrons, and that was that. A nice, tidy picture of reality. But nature, as it often does, had something more subtle in mind. Because it began to dig deeper into the behavior of these tiny particles. They started to notice patterns, symmetries, that suggested something curious. Equations that described matter didn't just allow for the particles we knew about. They also allowed for particles that looked almost exactly the same, except for one very important detail. The properties were reversed. Charge, for instance, could flip sign. Positive could become negative. Negative could become positive. Mathematical trick, it wasn't just a mathematical trick. It wasn't something you could ignore and say, well, that's just a quirk of the equations. And that was telling. But no, the mathematics was telling us something very real about nature. It was saying, if this kind of particle can exist, and so can its opposite. That led to another astonishing idea that for every particle of matter, there might be a particle made of something we now call antimatter. So what does that mean? Exactly that. Well, imagine taking an electron, a tiny particle with a negative charge that orbits the nucleus of an atom, and yet another particle that is identical in every way, same mass, same behavior. But instead of being negatively charged, it's positively charged. That particle exists. I call it a positron. It's not hypothetical. It's been created in laboratories and even shows up naturally in certain kinds of radioactive decay. Protons have antiprotons. Neutrons have antineutrons. And in principle, you could build entire atoms out of antimatter. Atoms, maybe even antimolecules, anti-stars, perhaps entire regions of the universe made of this strange mirror substance. Wild idea, but it follows logically from the same rules that govern everything else we observe. But here's where things get even more interesting. Matter and antimatter don't just coexist peacefully when they meet. When a particle of matter encounters its antimatter counterpart, something dramatic happens. They annihilate each other, converting their mass into pure energy. Not metaphorically, literally. It's one of the most direct demonstrations of the relationship between mass and energy that physics has ever revealed. So now we are faced with a puzzle that's both simple and profound. Laws of physics allow matter and antimatter to exist in equal amounts, and if they were likely created together at the beginning of the universe, then why do we see a universe made almost entirely of matter. Where did all the antimatter go? Or is it out there somewhere, far beyond what we can currently observe, quietly forming its own structures, quietly forming its own structures, starts its own version of reality. Now, if you start thinking about antimatter seriously, you quickly realize that it's not just some exotic curiosity sitting off to the side of physics. What you may be thinking, what you mean by reality itself. Because up until this point, we tend to assume that the things we see are the only version of things that can exist. The matter tells us that nature doesn't play favorites. It allows multiple versions of the same fundamental idea. What's especially fascinating is how antimatter was first discovered. It didn't come from someone accidentally stumbling upon it in a lab. It came out of pure thought, out of trying to make sense of the equations that describe how particles behave at very high speeds. When physicists were working out these equations, they found solutions that didn't seem to correspond to anything known. It was tempting to ignore them, to say, well, those solutions don't mean anything physical. So they took them seriously and asked a very simple question: what if they do? And when scientists finally went looking, they found exactly what the equations predicted. After appearing that antimatter wasn't just a mathematical curiosity, it was the real physical part of the universe. Let's see about the remarkable things about science. Sometimes, if you follow the logic carefully enough, nature reveals its secrets before you even perform the experiment. But once you know antimatter exists, the next question becomes, how does it behave? And here's where things are both reassuring and strange at the same time. It behaves just like ordinary matter. It forces in the same way. It follows the same physical laws, and if you didn't know better, you might not even be able to tell the difference just by watching it move. But yet, the difference shows up when you look at the details. The charges are reversed, certain properties flip, and most importantly, when antimatter comes into contact with matter, the result is not just a collision, it's a complete transformation. Particles vanish, and their place, you get energy, often in the form of high energy light. Destruction in the usual sense. It's more like a conversion from one form of existence into another. Now, that might sound dangerous, and in some sense, it is. But a small amount of antimatter contains a tremendous amount of energy. If you could somehow store and control it, it would be one of the most efficient energy sources imaginable. The moment antimatter touches the walls of any container made of ordinary iron, it annihilates. Scientists have to use clever techniques, like magnetic fields, to keep it suspended in empty space, never quite touching anything. And despite all this effort, we've only managed to которая длится с tiny amounts of antimatter, far too little to use for anything practical on a large scale. It's expensive, difficult to create, and even harder to store. Yet even in these tiny quantities, it has proven incredibly useful. Antimatter plays a role in medical imaging techniques that allow doctors to see inside the human body in ways that would have seemed impossible not long ago. Yet antimatter isn't just some abstract concept floating around in the record of physics. It connects deeply with experiment, with technology, and with our aim to understand the universe at its most fundamental level. And the more we study it, the more it challenges our assumptions, not just about particles, but about symmetry, balance, and why the universe ended up the way it did in the first place. And if you keep following this idea just a little further, you run into one of the most puzzling questions in all of physics, one that doesn't just sit quietly in the background, but keeps insisting that something about our understanding is incomplete. Antimatter is real. And if the laws of physics treat matter and antimatter almost exactly the same, then the universe should, in principle, contain equal amounts of both. Now, think about that for a moment. At the beginning of the universe, in the extreme conditions just after the Big Bang, Energy was being converted into particles constantly. Due to the rules we understand, every time a particle of matter was created, a corresponding particle of antimatter should have appeared alongside it. Like nature was keeping perfect balance, making sure that nothing was favored over anything else. But when we look out into the universe today, that balance doesn't seem to be there. Everything we observe, stars, galaxies, planets, even the air we breathe, is made of matter, antimatter on the earth, rapid, incredibly rare. We can create it in laboratories, and we can detect small amounts of it in cosmic rays, but we don't see entire regions of space made of antimatter in the way we might expect. Somehow, out of what should have been a perfectly symmetrical beginning, a tiny imbalance developed. A tiny imbalance, just a little more matter than antimatter, was enough to shape the entire universe as we know it. Because when matter and antimatter met, they annihilated each other, leaving behind only whatever small excess remained. And that leftover matter is what everything around us is made of. That raises a very big question. Why was there an imbalance at all? What caused the universe to choose dark over antimatter? Physicists have been working on this problem for decades, and while we have some clues, we don't yet have a complete answer. Like weather, there are subtle effects, tiny asymmetries in how certain particles behave that might help explain it. They don't seem to be enough to account for the enormous difference we observe. This is where things become really interesting, because it means that antimatter isn't just something we study to understand particles. It's something we study to understand why we exist at all. Balance had gone the other way, or if it had remained perfectly equal, the universe would look completely different. Событие, которое длится 100 лет, matter left to form stars, low chemistry as we know it, no structures that could give rise to life. That we give a very fact that we're here asking these questions suggests that something unusual happened in the earliest moments of the universe. Something broke the symmetry. And that break, as small as it might have been, had consequences that echoed across billions of years. Antimatter. We're not just talking about antimatter. We're not just talking about exotic particles or high energy experiments. We're about a key piece of a much larger puzzle. A puzzle that connects the smallest scales of physics with the largest structures in the cosmos. A reminder that even the tiniest differences in the laws of nature can lead to vast and unexpected outcomes, and that the universe still holds mysteries that challenge not just our knowledge, our intuition. And if you look at all of this together, the existence of antimatter, the strange way it mirrors ordinary matter, the imbalance that seems to define our universe, you start to get a feeling that nature is playing a very subtle game. Not a game in the sense of something trivial, but a kind of deep sense of something trivial, but a kind of deep structure where которые truths give rise to unexpected consequences. One of the things that makes antimatter so fascinating is that it challenges our everyday intuition at every step. In our daily lives, opposites don't usually behave in such dramatic ways. Two objects that are similar but slightly different, they might interact, they might collide, but they don't typically disappear in a flash of energy. And yet, at the level of fundamental particles, that's exactly what happens. Matter and antimatter don't just cancel each other conceptually, they literally transform into something else entirely. But now, to really appreciate this, you have to think about what we mean by a particle. In the first place, it's very tempting to imagine particles as tiny solid objects, like little billiard balls bouncing around. The picture, while useful at times, isn't quite right. In modern physics, particles are better understood as excitations of underlying fields, disturbances that carry energy and momentum. Antimatter fits into this picture naturally as another type of excitation with properties that are related but reversed. So instead of thinking of antimatter as something completely foreign, you can think of it as another expression of the same underlying reality that rules, the same set of rules, the same framework, but with a different configuration. The universe has a kind of built-in symmetry, allowing it to generate both versions from the same fundamental principles. And yet, the symmetry is not perfect. It makes the story so intriguing. If it were perfect, we wouldn't be here to talk about it. That it's slightly broken suggests that there are deeper layers to the laws of physics that we don't fully understand yet. Seeing a pattern that almost repeats, but not quite, and that small deviation hints at something more fundamental beneath the surface. When designing experiments to probe these differences with incredible precision, how matter and antimatter behave under the same conditions, looking for any tiny discrepancy that might reveal new physics. Even the smallest deviation could provide a clue, a hint about what happened in the early universe and why the balance tipped the way it did. Sometimes there's a practical side to all of this. Antimatter, despite being rare and difficult to handle, has already found applications in technology. It's a stole, where it's used in certain types of medical imaging that allow us to observe processes inside the human body with remarkable clarity. In these cases, the annihilation of matter and antimatter becomes a tool, a way of generating signals that we can detect and interpret. But beyond its applications, antimatter represents something deeper, the reminder that the universe is not limited to the forms we're familiar with. There are possibilities encoded in the laws of physics that extend far beyond our everyday experience. And by exploring those possibilities, we don't just learn about particles or equations. We expand our understanding of what reality itself can be. Perhaps the most interesting part is that we are still in the middle of this exploration. We don't have all the answers. There are still open questions, still mysteries that resist simple explanations. And that's not a failure of science. It's the very thing that drives it forward. The answer question is an invitation to look deeper, to question assumptions, and to refine our understanding of the world in ways that we couldn't have imagined before.